on reciprocity. Oh, good. And first of all, I'd like to thank all the wonderful Miller staff, Hillary, Verinda, and others, and my coaches, Sunon Che, Samuel Hopkins, Dan Ibarra, and Antoine Cole. And in the picture is Gauss, who is the grandfather of reciprocity laws, as you will see. And here's an overview of my talk. The first two sections will be background sections on solving equations in number theory and modular arithmetic. And last two parts are going to be the main contents, quadratic reciprocity by Gauss and the conjectural general reciprocity by Langlands. And in the pictures are a 17th century copy of Dauphintis's book on arithmetic. And this is his old Chinese text on modular arithmetic from the 3rd century, but I think it's a Qing dynasty copy. And Gauss, and unlike Gauss, Langlands is still alive, and he's a professor emeritus at the Institute for Advanced Study in Princeton. All right, so here we go. Well, a key problem in number theory is to find all integer solutions of an equation. So, well, in math is all about solving equations in some sense. We're particularly interested in integer solutions. So for example, here's a non-trivial but interesting enough example. The equation is x squared plus y squared is z squared. And well, if you try to solve this over real or complex numbers, then it's quite different. For instance, if over real numbers, you just take the square root to solve this equation, but over integers, it's quite different. And it's not so easy to find solutions, although there are some well-known examples like 3, 4, 5, because 3 squared plus 4 squared is 5 squared. And there are some others you can find. And in this case, it takes some work, but it turns out that we can identify all solutions, all integer solutions. And yeah, there are infinitely many, in fact. But if you just tweak this equation a little bit, then it becomes very, very hard. Just let's say you just go from x squared to x to the nth power and consider this equation, x to the n plus y to the n is z to the n. That's known as Fermat's theorem, which is the statement that has no solutions, integer solutions at all, if x, y, z are non-zero. And the key point here is that n is greater than or equal to 3. The previous case is n equals 2. So, well, it took more than 350 years. It was first suggested by Fermat in 1637, but then, but then it was settled in 1995. And as you can see in this example, yeah, you just change the equation a little bit and then it becomes almost impossibly difficult. And you can consider all kinds of equations, right? These are just examples, but you know, you can consider equations or a system of equations in several variables. And well, in general, it's simply too hard in general. But the point of my talk today is that we can still get a handle on these equations if we consider the same equation in modular arithmetic. So now I need to tell you what modular arithmetic is about. By the way, I mean, it's such an equation where we try to find integer solutions of an equation. These are called Diophantine equations after Diophantus. So here's the setup for modular arithmetic. We have integers a, b, n, where n is greater than 0, or when n is 1 is uninteresting, so we may as well say n is greater than 1. And the basic definition here that of congruence modulo n is pretty simple. You consider two numbers congruent if the difference is divisible by n. And in that case, you just write a is congruent to b mod n in this way. So the simplest example is when n is 2. In this case, well, every even number, if you think about it, is congruent to 0 because the difference is divisible by 2. And every odd number is congruent to 1, modulo 2. So in some sense, there are only two numbers, 0 and 1, just like, that's how you would communicate with the computer, right? There are only 0 and 1s, and then you can actually add and multiply numbers just like you would to integers. For instance, even plus odd is odd, and odd plus odd is even, or odd times odd is odd, things like that. So in general, for more general n, in mod n arithmetic, the way to think about this is, given a number, you can always think of that, divide the number by n, and then take the remainder. And that way you can identify any integer with something in this set from 0 to n minus 1, and you can perform addition and multiplication and other interesting operations, right? So here are some examples. If you think of numbers modulo 10, that means you only care about the very last digit. So 107 is just congruent to 7, but you can go to negative numbers. So 7 is congruent to -3 or -13, right? And you can do the multiplication. 2 times 4 is 8, but 8 is congruent to 1 if you consider modulo 7. And well, even number square root is 0 mod 4, odd number square root is 1 mod 4. This takes a little bit of thought, and I can quickly prove this. So even number, you can write it like 2k, k is an integer, then that's 4k squared. So that's divisible by 4, which means that it's congruent to 0 mod 4. And odd number can be written as 2k plus 1. And then if you square, that is 4 times something plus 1. So that's congruent to 1 mod 4. So that's how you see it. And one important point I'd like to make is that, well, maybe unknowingly or knowingly, you have been using this all the time. It's all around us. When you're a very young kid, if you're counting with one hand, then that's like doing mod 5 arithmetic. And if you think about 7 days a week, or hours or minutes, then you're secretly doing mod 7, mod 12, or mod 60 arithmetic. I hope that makes sense. And if it does, then I like to use this idea to do some math problem. Math consists of theories or theorems, but also exercises. And some people say that a math sum must contain a proof. And well, as a mathematician, I like to prove things. So here we go. The problem is that this equation here has no integer solutions. Well, there's one computational way to see this, because squares are non-negative. So you don't need to check infinite many possibilities, but if x and y are large enough, then certainly it's not going to work. So for instance, x, you can let x go from 0 to the square root of this number and then check case by case. That's one way. But as a human being, there's a more clever way. And the observation is that it's enough to show that this equation has no solution modulo 4. Has no solution. Well, why is this? Because if you had a solution, then, well, if A is equal to B, then of course A is congruent to B modulo 4, right? So equality gives you congruence. So if you take the contrapositive, then what we're saying is, if this has no solution, then the original guy would have no solution. So here we go. So that's a weaker statement, but if this already has no solution, then we are done. But now, think about x squared and y squared modulo 4. I just told you that if an even number squared is 0 mod 4 and an odd number squared is 1 mod 4, and every number is either even or odd, which means that x squared and y squared are 0 or 1 mod 4, which tells me that if you add them up, then the only possible numbers are 1, 0, 1, or 2. But now look at this number. This number, what is it mod 4? Well, if you divide by 4, then really 100 is divisible by 4. So you just pay attention to the last 2 digits, and you can easily see that this is 3 mod 4. Whereas, well, here, 0, 1, 2 are not equal to 3 mod 4. So we are done. Because x squared plus y squared is never congruent to 3. So this thing has no solution. So the point of this proof is that, well, if you want to study Diophantine equation to see whether something has an integer solution, it's very useful to consider the same equation modulo some number. Modulo 4, it could be modulo some other number, but in this particular example, mod 4 works well. Okay, so I hope I made the point. So now we go to the main contents. So basically, what I like to do is to solve an equation in modular arithmetic. So, and let's start with a single variable equation. And the first case is a linear equation, right? A degree 1 equation. That turns out to be easy. And the next case is a degree 2 equation or quadratic equation. And when you try to do this, the basic case is to find a square root. You want to solve the equation of the form x squared equals something, modulo a prime. So this is what we are going to do. So for this, let PQ be distinct primes, odd primes, and Q is 1 mod 4 for simplicity. You can do this more generally, but then statements are slightly more complicated. So I'll just avoid that. And here's a cool fact. Well, I told you that modulo P, basically the numbers are 0, 1 up to P minus 1. All numbers are these numbers. And then you can ask which of these have square roots, right? And if you think about the analogous situation in real numbers, then, well, what happens? Well, non-negative real numbers have square roots. Negative real numbers have no square roots. And somehow similarly, here exactly half of the numbers have square roots. So just as a quick example, if I take modulo 7, then there are only 7 possible numbers. But 0 is not interesting. 0 certainly has square root, so just disregard that. And from 1 to 6, which one has square roots? If you think about it, 1, 2, and 4 have square roots, and 3, 5, 6 have none. For instance, 2 is a square root because 3 squared is 9, which is 2 mod 7. Okay, so the surprising theorem by Gauss says the following. It's really a fun theorem if you think about it. It says that, recall that P and Q are distinct odd primes. Now, Q is a square modulo P if and only if P is a square modulo Q, right? And well, this is surprising because, well, this equation has little to do with this equation. For instance, if you know the solution to this, can you give a solution to this? Well, it's not clear at all. And in some sense, it's like saying that different primes P and Q are talking to each other. While, I mean, there's no clear reason for them to do so. So just an example of this theorem is, well, for some small primes like 3 and 5, you just see that 5 is not a square mod 3 and 3 is not a square mod 5. You can just check. In this case, both are negative, so both are false. So the theorem is still true. A more complicated but fun example is the following. I like to see that 5 is a square modulo this huge prime number, which I've taken from some table. And how do you check this? Well, you can try to go through all possible values of x, right? X could run from 0 up to this number minus 1, and then well, just check case by case and try to see if there is a solution. But using quadratic reciprocity by Gauss, there's a better way, and you don't need a computer for this, which is that you can basically switch the roles of P and Q. So in this case, it's saying that this has a square root if and only if some huge number I have here has a square root modulo 5, right? But then, well, what is this number? Modulo 5. Modulo 5, because 10 is divisible by 5, you only need to pay attention to the last digit, which is also 4 mod 5. But then if you think about the very last statement, this is pretty easy to see that it has a solution on the nose, namely x equals 2, for instance, right? So because this number is a square root mod 5, 5 is a square root modulo this huge number. So that's one application of quadratic reciprocity. Okay. So, well, what did people think about afterward? Well, it's certainly a cool statement. So people wanted a generalization, because any important mathematical fact or cool math fact can't be a coincidence, but there should be some bigger picture. So that has taken up many mathematicians in 19th century. And one obvious direction of generalization is to go from a quadratic equation or square root to a cubic root, fourth root, etc. And people did investigate that, but somehow what people weren't satisfied enough. So even in 1900, we didn't have enough understanding. So Hilbert suggested this as one of his famous 23 problems. And simply put, the question is to find the most general reciprocity law. It's kind of open-ended question. So I need to steer you in some direction, not to be too vague. And one thing we see from here is that it's about solving an equation modulo prime. And my viewpoint will be that I want to give an equation as an equality. So in quadratic reciprocity, I'm interested in the equation x squared equals q, but then I want to consider this equation modulo different primes. So this prime, this varies, and then this equation is kind of fixed. X squared equals 2 is fixed. And fix an equation, count the number of solutions modulo different primes, and by counting number of solutions, I get a string of numbers, right? Modulo each prime. And I want to know whether that information is captured by something else in mathematics. And the right-hand side in quadratic reciprocity, it came from another equation, a different equation like x squared equals p. But in general, we want to be a bit more open-minded. It could be something else, but we don't know where it might be coming from. And actually people wondered what this could be. So I just copied the equation, and copied the form of the problem. And it's instructive to consider the following more complicated example, a two-variable equation now, but still simple enough, y squared plus y is x cubed plus x. And it's called an elliptic curve because if you plot the solution set, then, well, for instance, over real numbers, then it's this curve. It kind of looks like this. And over complex numbers, the solution set looks like this because a complex dimension 1 is real dimension 2. And, well, you need some work to plot that, but that's what it looks like. But again, we are trying to understand the solutions modulo primes, integer solutions modulo prime. So it's quite different. But the main advantage is that instead of drawing pictures, you can actually count the number of solutions. Because what does that mean? Well, modulo 2, here's a table, but modulo the prime 2. What do I mean by counting the number of solutions? In that case, x has values 0 or 1, and y can take values in 0 or 1. So there are 4 possibilities, and just plug in every possible combination and check whether this equality holds modulo 2. And in this case, all 4 cases are solutions modulo 2, so you just count that number. But in general, modulo 3, then you will have 9 cases, and then only 6 of them will be a solution, modulo 3, and just keep going to make this table. But then the question is, well, what's on the left-hand side is now these numbers. You just count the number of solutions modulo each prime, and then is there anything that encodes these numbers somehow? Well, it's like you're in biology, maybe you're reading a gene of something, and then you want to find the same gene in some other, well, animal or whatever. It turns out that, I mean, these numbers somehow appear in a completely different context. It turns out that these numbers appear as coefficients of a modular form. I'm going to explain what it is, but it's a power series. It's a kind of infinite series in the variable q, and then these coefficients somehow capture these numbers in the sense that the pth coefficient AP has to do with the number of solutions modulo p for every prime p. So that's exciting. And again, I mean, it's striking because modular forms come from a completely different source than the equation you started with. But I owe you an explanation of what modular forms are about. So I can't give you a complete account for sure, but let me try to say something to give you a feel for what this is all about. But following my coach's recommendation, I need to first clarify that modular in modular form has nothing to do with modular in modular arithmetic. It's just a coincidence of terms, but they're different like an apple and an orange, right? So what is it? Well, a modular form is some well-behaved nice function. It's an analytic function, in fact, on the complex upper half plane. So the domain of this function is, I mean, this is complex plane. You just imagine that. And then it's defined only above the real axis. So that's the upper half plane. And which satisfies some nice equations like its translation invariant or periodic. And also there's some other properties. It's kind of self-replicating property in the sense that, well, translation invariance basically means if you, in the complex plane, if you move by one to the left or to the right, then the value of the function is the same. But also you can kind of propagate the values in the sense that these equations somehow allow you to determine your function. If you know your function on this domain, then you can determine the function values everywhere else, even below. So roughly speaking, it's such a nice function, well studied in mathematics. But to make connection with the previous page, basically this periodicity tells you that there's a power series expansion. A periodic function can be written as a linear combination, possibly infinite combination of exponential functions, roughly speaking, by Fourier theory. That's where these numbers come from. It's a little complicated, but modular forms appear in many different places of math. But the main point is that there's no clear ties with the equations we are considering. And that's why it's all striking, because we just seem to be discovering that two things which are seemingly unrelated can be very closely related. So that brings us to the far-reaching conjecture by Langlands, which roughly says that for each equation E, there's a corresponding modular form such that the number of solutions modulo P has to do with P's coefficient of the modular form at every prime P. And well, of course, this is a conjecture and it's almost an equality in general. It's just a simple relationship you can explicitly write down. But for this talk, you can just consider them equal and it doesn't do any harm. But I'm putting these words in quotation marks because, well, to be precise, you need to really consider some generalizations of these notions. And well, that has fascinated me for a long time and been central theme of my research. And as for the conjecture, well, there's still active research going on by many people and increasingly more instances are known nowadays, but still it's largely open. And there are many problems to do. Let me quickly say why I think that's important. Well, the first reason is that, well, it's kind of beautiful statement, just like quadratic reciprocity, and especially the attractive point is that it relates to mathematical objects that are seemingly completely unrelated. And from the practical viewpoint, it also kind of transfer information, allows us to transfer information, and that's critical to solving open problems. Oh, I guess it's about time. So yeah, basically what that means is that we have this string of numbers here and string of numbers here. And the what you can learn about these numbers can be quite different. You learn about these numbers, learn something about these numbers from the left-hand side, and you can transfer that information to the right-hand side. And also you can learn about these numbers from the right-hand side from the fact that they're coming from modular forms, and then you can transfer the information to the left-hand side. And by going back and forth, you basically increase the amount of your knowledge, and that's critical to solving open problems. Although this sounds a bit vague, let me just give you a quick example and finish. So that's a summary slide where I restated the Langlands reciprocity conjecture, which was motivated by the prototype of quadratic reciprocity. And in particular, it allows us to settle Fermat's theorem as a special, for which a special instance of this reciprocity law turned out to be enough. But it also has implications outside of pure math, such as constructing expander graphs, Ramanujan expander graphs, or the so-called S-duality in mathematical physics. But it's really, it's about time to finish. So thank you for listening. That's the end.